Hello. Hello.
Yes, sir.
Yes. What about resource person has not joined?
Not
Resource
at
person.
not at kitchen, sir.
Who's the in charge for the today's resource person?
Thank you, ma'am. Yeah. Very good evening to one and all present here. It is with great pleasure and pride that I extend a warm welcome and heartfelt welcome to each and every one of you to this prestigious faculty development program organized by the Department of RF and Communication Systems, SIMATS Engineering. The theme of our 6-day FTP is Intelligent VLSI, the convergence of AI, signal processing and computing. Today, we are especially to have a Dr. Vijay Kumar sir, Professor at the School of Engineering, VIT Chennai, as our resource person for the day 4. His session on VLSI implementation of cryptographic algorithms will undoubtedly be a valuable learning experience for all of us. Once again, I am welcoming to this 6 days FTP on Intelligent VLSI, and it continues by I am continuing by the introduction of our guest speaker, Dr. Vijay Kumar sir. We are honored to welcome Dr. P. Vijay Kumar sir, Professor at the School of Engineering, School of Electronics Engineering, Vellore Institute of Technology, Chennai, with a distinguished academic background. He earned his PhD in Wireless Communication and Network Security from Pondicherry University and holds an MTech from Pondicherry Engineering College and BTech from Rajiv Gandhi College of Engineering and Technology. Dr. Vijay Kumar sir brings over 17 years of experience in teaching and research with a prolific record of publishing more than 60 research papers in Scopus Sciendex journals and conferences. His research areas are AI with cybersecurity, hardware security, cryptographic algorithms, machine learning, blockchain security, IoT security, and 5G, 6G network security. He has contributed significantly to innovation with over 10 patents filed, published, and granted. Dr. Vijay Kumar sir is also recognized as a member of professional bodies such as ISTE, IET, CSI, and IAENC. And he also serves as an associate editor, advisory board member, and board of studies member across reputed platforms and institutions. We are privileged to have here, sir. So again, I welcome to Dr. Vijay Kumar, sir. Sir, are you here? Sir? Now the floor is yours, sir. Dr. Vijay Kumar, sir.
Yes, thank you. So I hope I am audible.
Yes, sir. You are audible, sir.
Yeah. Yeah, good evening to all. So thanks for the introduction. So currently we are working on implementation of quantum cryptography using AI. So and also we are working on AI with cybersecurity and also security by blockchain technology. So along with our implementation technology like VLSI as well as other new IoT technologies we are working on. So now come to the topic. The topic given to me is VLSI implementation of cryptographic algorithms. So here there are different types of cryptographic algorithms are there. So in this session, I'm going to tell you what are all the new as well as emerging cryptographic algorithms are available and how it is implemented in VLSI and which is best cryptographic algorithms for different applications. So that is the thing we are going to discuss in today's session. So before we go into see the emerging cryptographic techniques, first we'll see a small introduction about cryptography and its types, and then we go on how to implement it. So cryptographic algorithm is useful to give you the secure communication in different networks like 5G networks as well as IoT networks also, as well as blockchain networks also. Sometimes it plays a role in wireless multimedia communication also. So in our research work, what I did is especially for blockchain network as well as IoT also we did, and also many cryptographic protocol we developed specifically to give the services like authentication as well as maintaining the integrity as well as maintaining the confidentiality of the data, okay, as well as the privacy of the users. Okay, so purpose we are using the cryptographic algorithm. So each and every work what we carried out is going to give you different services actually. Now come to the point. Cryptography is nothing but it will help you to convert your original message into the different form, or it will helpful to convert your the information which is confidential into the indeterminate format. Okay, so that is the role of your cryptographic technique. So as a cryptanalyst, you can able to you can able to work on different aspects, and then you can able to study how the particular algorithm can be broken. Okay, how otherwise how that particular algorithm should is unbreakable by the eavesdropper. Okay, so that type of studies you can able to carry out by the cryptanalyst. So and also we have the term called crypto system. So crypto system is nothing but that is used to convert your original information into the process of conversion of your original information into the different form, okay, or indeterminate form by using the key. Okay, and also by involving some algorithms, okay, step-by-step procedures we have to use to give you the better outcome. Okay, so that is use of your crypto system. There are two types of cryptography techniques are there. One is symmetric key cryptography, or it is called as private key cryptography, and other one is asymmetric key cryptography or public key cryptography. So in our symmetric key cryptography, as I mentioned, in a crypto system, we need some particular key to involve in the algorithm, encryption algorithm, to develop the new ciphertext. Okay, so the same key if you use at the transmitter side as well as the receiver side means then it is called as symmetric key cryptography technique. Mostly what will happen is they will use the key called a secret key, which is plays a role in both transmitter as well as receiver side. Otherwise it is called as private key. It also has a, because private key is also a secret key actually. These also have the name called secret key. So if the transmitter as well as the receiver will involve the same key at the transmitter as the receiver side means then that is called as private key cryptography. And other one is public key cryptography. Here at the transmitter side for encryption purpose they involve a public key, because here they are involving two different keys for encryption as well as decryption. So one key they use it for encryption purpose, and another key is used for decryption purpose. In encryption purpose, if they involve a public key means then it is called as public key cryptography. And obviously what will happen, the private key is involved in receiver side to decrypt data. So what exactly the encryption and decryption is nothing but these are the two different processes are involved here. That is a set of rules, a set of protocols they are telling that and how the data are transmitted from one form to another form. That is called as your encryption decryption process. So there are different keys are involved in our encryption and decryption process. Then that is called as public key cryptography. If the same keys are involved in both the transmit receiver side as well as encryption and decryption process, then it is called as symmetric key cryptography. And there are different algorithms are there. Okay, especially the data encryption standard algorithm, as well as advanced encryption standard algorithm, as well as triple DES algorithm and message digest algorithm, or the different algorithms are available to use the key the same as well as private as well as transmitter as well as receiver side. And the other one is asymmetric cryptographic algorithms like RSA algorithm, elliptical cryptographic algorithm, and hyperelliptical cryptographic algorithms. So these are very famous public key cryptographic algorithms are there, and many bank sectors, many website developers, they are using these algorithms to give the secure communication over the insecure channel. Okay. And the reason why they always prefer asymmetric key cryptographic algorithms compared with symmetric key cryptographic algorithms, if any key is compromised in symmetric key cryptographic algorithm, then what will happen? The entire system is in insecure position. So that's the reason they always need two different keys they want to involve in their secure communication process. So compared with your symmetric key, asymmetric algorithms will now it is very famous, and many researchers, they are working on this particular algorithm, and also they want to improve some, they want to add some novelty in this particular algorithm, and also they want to implement this algorithm in different networks as well as different scenarios, okay, different use cases. Okay, so that's a major thing. So here the diagram, it shows you the two keys are the same keys. So see here secret key here, and also here also secret key, and these secret keys are used in plain text. Okay, and that is used to encrypt the data, and the resultant data is ciphertext. And again, what will happen in the symmetric key encryption algorithm? Again, they are using same secret key to get the data back. Okay, so here small mistake will be there. So the secret key has to come here. Actually, the symmetric key encryption algorithm has to come here, and this is asymmetric key cryptography technique. Again, at the transmitter side, private key is involved here for asymmetric key encryption algorithm, as well as public key is involved at the receiver side for asymmetric key decryption algorithm. So here there are two different keys are involved here. So if any one key is compromised as a user-dropper, they are not able to get the data very easily in the network. Okay, so that's the reason they always look into asymmetric key cryptography technique compared with symmetric key cryptography technique. So among other cryptography technique, your elliptical cryptography technique is a very famous one because it has a very smaller key length of only 160-bit key size. Because if you use RSA algorithm, it requires 1024-bit key size for providing the security for the system. So, but the same level of security we can able to achieve in our ECC-based cryptographic algorithm. So that's the reason it is very famous. And the other thing is, if you involve lesser number of key length, automatically what will happen? The number of keys involved in the transmission is also very less. Okay. So communication bit is also very less in our ECC. But if you go for RSA algorithm, since the larger in key size, so it the process outcome is also require more number of communication bits to transfer between the transmitter and receiver. So that is also one of the drawback. So if you have more secret key, as well as you are involving more number of keys for the communication process, then definitely what will happen, the communication overhead will be there. Okay, and the other thing is, if you talk about RS algorithm, there we are using the exponential logarithm problem. Okay, because we have the formula called x power y mod p, something like that. Okay, so here we are always using the exponential logarithm problem. Okay, so that will compared with the operations like addition, subtraction, multiplication, division, your exponentiation will require more amount of data, more amount of time, as well as more amount of power also it require. Okay, so computationally also will have the overhead in our RS algorithm. But if you go for ECC, we are not involving any operations like exponential algorithms. Okay, e power x or x power y, whatever it is. Only we are involving only addition operation only. So you know very well how the addition operation is. What I call addition operation is very easy compared with the other operations. So that is a major purpose of the ECC is very famous among other cryptographic algorithms. So other thing is we can able to use a private key for encryption and public key for decryption, and vice versa. We can able to use the public key for encryption and private key for decryption. That is also we can it's possible. And the how this particular ECC is very secure means because of elliptic curve discrete logarithm problem. So what is the elliptic curve discrete logarithm problem is? So we are having the private key. So that particular private key is generated by the end users. Okay, as the end user, suppose you want to transmit any data. Okay, suppose you want to you want to involve in network to do the secure transmission. Means then as a end user you have to generate you have to hold the private key which is very secure one. Okay, so it is not known to any others. So use some process you have to generate your algorithm. You have to generate your private key, or you have to randomly generate some number and then you have to keep it with you. Okay, so that particular private key here is K, and other one is we have the P. P is nothing but point on the elliptic curve. So in ECC we always talk towards the elliptic curve. So the elliptic curve is nothing but y square mod p equal to x cube plus ax plus b mod p. So this particular elliptic curve is one of the famous prime elliptic curve. This particular elliptic curve we are using, and then we are going to generate the elliptic curve points from the elliptic curve, and that point is going to act as the generation of the public key for the elliptic curve crypto system. Okay, so if anyone knows the value of your private key, okay, and for nothing but your public key, okay, so they are not able to get back the private key because which is already involved in some particular process. Okay, and then it is converted into the public key, so they are not able to recover the private key from the public key. That is a major advantage of your ECC. So Q equal to K into P. For example, K is private key, and then P is any point on the elliptic curve. So you have to choose any one point on the elliptic curve. That particular point is going to do the scalar multiplication process with the value K, which is a randomly generated private key value, and as a result, the public key point will be generated. Okay, so that public key only they are going to use it for the encryption process, and then at the decryption process, user they already have the private key. So using that particular private key, they will decrypt the data. Okay, but the problem here is the advantage here is suppose public key is compromised or known to any user. Okay, because public key is always known to users, other users who are the network, but they are not able to get the data very easily. Okay, because of we are not able to get back the private key very easily from the public key. So that's the reason. Next one is this is the equation what we have. Okay, so S square equal to RQ plus AI plus B. So here actually instead of X and Y, I using here R and S. That's it. Okay, so these are the two variables which are used in the elliptic curve equation, and also other two variables are A and B. So A and B are the what you call as Abelian group. Okay, these are the values which is come under the Abelian group. Okay, and which has to satisfy the condition 4AQ plus 27 B square Q should not be equal to 0. So the A and value, B value we have to choose. So that particular A value, B value will plays a role of the size of the curve. So once the size means structure of the curve. Okay, so once the structure of the curve is decided, then what will happen? Easily you can able to generate the public key. Okay, by using the point on the elliptic curve. So we have to first choose the value of your A and B. Okay, and which has to satisfy the condition 4AQ plus 27 B square should not be equal to 0. Similarly, we have to place some values. Okay, for example, placing some value for R equal to 1. Okay, and the equivalent value of S has to be come. Okay, then similarly we have to use some value for R, and then the equivalent value you have to get it for S. So that particular pair point will be going to have the role in our elliptic curve cryptography, elliptic curve structure. Okay, so like this what will happen, we have to choose different values of R, and then the simultaneous value of S we can able to get by choosing the value of A and B. Okay, properly based on the condition whatever given. So like this what will happen, we can able to feed the value in this equation, and then we are going to arrive the set of points from the equation, and that particular point is going to use it to use it for generation of your public key. So if you want to involve more number of users in the network, then you have to generate more number of points on the elliptic curve. And then how it is possible means you have to use more parameters, nothing but for example here what we worked is we use prime number is 13. So by for 13 prime number values, the different set of points are generated here, and then those points are used for the public key generation for the users. Okay, so probably we can able to get 13 to 18 user points we can able to generate from this elliptic curve. Okay, so as a result of this generated point, then they can able to generate the public key for the users. Okay, so that particular prime number plays a role here. So the number of value what is chosen for your prime number will have two advantage. One is that will allow the user to generate more number of keys for the end users, and the other one is if you go for larger prime number, what will happen, the security of the particular systems also get improved. Okay, so that is also the advantage. Okay, so come to the types of elliptic curve. So there are different types of elliptic curves out there. Elliptic curve over real number, over prime number, over Cavali's field. So how these three elliptic curves are differ with each other is only because of the elliptic curve equations only, and the parameters, okay, variables involved in the equations will be different, and this other what will happen, the structure also will get different, and then amount of values generated from the empty curves also get different. Okay, so this is the equation, first equation. So S square mod P equal to R cube plus AR plus B mod P. So this is the equation what we used for our prime field, what we implemented in VLSI code also we wrote, and then we proved that which particular FPGA will have a better result for ECC over prime number. Okay, and the other one is over binary field. So S square plus RS equal to R cube plus ER square plus B. Okay, so these are different curves are there. So we will choose any curve to generate your points, and then we will use those points for the encryption and decryption process. Okay, so this is some arithmetic operations we are involving in our empty curve. So small example we given here. For example, A value, B value we choosing is 1 and 1, and then prime number is 13. Okay, so choosing the value of 13. Okay, as well as choose the value of A and B and 1 here. Okay, and after that we have to change the value of R from 1, 2, 3, 4, 5, 6, 7, 8 up to 13, and simultaneously the equivalent value of S we need to obtain here. Okay, so that is the arithmetic operations involved on empty curves. Okay, so here the point A and B is nothing but RA comma SA, and B is RB comma SB. Okay, and the resultant value is RC comma SC. So what exactly these two parameters says is we are going to generate the third point, okay, by adding the 2 points. Okay, what is the reason for adding the 2 points here is you know that Q equal to K into P. So here K is nothing but number of private key, and then P is nothing but the point on the empty curve. So the K value, for example 5, and then the point what is chosen on the empty curve is 5, 10. Okay, so 5 into 5, 10. So this is not the normal multiplication, this is a scalar multiplication. So this particular scalar multiplication can be replaced by a point addition process. So what is point addition is nothing but we are having some formula, okay, that will help you to add 2 points, and then that is going to help you to generate the third point. Okay, so what is the use of generation of the point here is using that point only we are going to encrypt the data as well as decrypt the data. So in elliptical cryptography, everything is considered as point, not only the key and also the messages whatever we are having, that is also we are going to take it in terms of points. Okay, so what exactly will give us output is we can able to get the pair of ciphertext point. Okay, that is the result will come after we execute your elliptical cryptography algorithm using your VLSI, Gorilla code or VHDL code, whatever it is. We can able to get a set of a pair of points we can able to get as a ciphertext. Okay, so after this particular ciphertext generation, okay, so we can able to send it to the receiver side, and they will apply the decryption algorithm, and then they will recover the information also in the form of point only. So that again, that particular point again they need to convert it into the original message. Okay, so here we are having the messages in the form of stream, nothing but the form of plain text, or that nothing but it consists of ASCII values, it consists of numbers, symbols, something like that. Okay, so we need some particular procedure to convert your message into point. Okay, and also from the point into message. So for that we are having the method called the Goblis method. So Goblis method or Goblis algorithm, whatever you call. So that particular algorithm will help you to convert your original messages into plain text point. Then that particular plain text point is going to be employed in the ECC encryption algorithm, and then that particular algorithm will generate the pair of ciphertext point. Then that particular pair of ciphertext point is transmitted, and then at the receiver side, that pair of ciphertext is again converted into plain text, okay, and that particular plain text point again converted into the original message, okay. That is also carried out by the Goblet's method, okay. So in this particular process, which is the major operations involved is point addition, okay. So I will show you. So wherever we are involving the elliptic curve encryption algorithm, as well as elliptic curve based digital signature algorithm, or elliptic curve based key exchange algorithm, everywhere, okay, you need to do the operation called the point addition, okay. So for that point addition formula is I'm showing here. So initially what will happen, whatever the point you took, okay, for example I told you 5 into 5 5 into 5 comma 10 is the scalar point multiplication process. So here, instead of doing the scalar point multiplication process, we are going to give you the equal operation called point addition as well as point doubling operation. So why it is called point doubling is the thing, but so you know very well initially there are two keys, 2 points are involved. So that 2 points will go for the point addition process. Then what will happen? The resultant value is stored in the some particular variable RC and SC here. Okay. So the 2 points initially what will happen? The involved here is 5 comma 10 plus 5 comma 10. Again what will happen? The resultant value is going to add with again 5 comma 10. Again the resultant value is going to add with another 5 comma 10. And again that resultant value is going to add with another 5 comma 10. Okay, so totally what will happen is 5 times 5 comma 10 is going to add it, okay, using this formula, and then the resultant value is stored in the variable RC and SC. Okay, so before you are going to perform this one, first thing is you have to decide whether it is a point doubling operation or whether it is a point addition operation. Okay, so how you can able to decide means by checking the value of your x coordinate and y coordinate of the 2 points. Okay, if x coordinate and y coordinate x1 y both are equal, similarly x2 and y2 are both are equal, then it is considered as we have to involve the point doubling operation. Okay, so that particular point doubling operation has to be performed at the initial stage. Then later what will happen? Point addition operation has to be performed, okay, by using this formula. Okay, and see here, these are all the steps we have to use to convert your plain text into plain text point, okay, by using the Goblet's method. So first thing is again we have to take one particular curve. We have to decide first which is the curve we are going to take to do the process. Okay, that is the first step. So you have to consider the equation, one prime elliptic curve equation. Okay, so this equation I considered, and I took 13 as a prime number, and the a value is 1 and b value is 1, and these two values has to be taken under the condition of 4aq plus 27b square. It should not be equal to 0. Okay, so a set of points should be generated here. So a 0 comma 1 and then 0 comma 12. So these points are generated by substituting the values of your r here, okay, and then alpha equal to 1 as well as beta equal to 1 here, okay, as well as do the operation of a mod. Okay, so everything we have to do, and then we have to get the values of 0 comma 1 0 comma 12 like that, okay, until the 13 values we have to do. Okay, so this set of points I generated from this equation with the assumption of these values here, and satisfy the condition 4aq plus 27b square should not be equal to 0. Okay, okay, so now consider that we have a set of points now, because the points are very important for the elliptic curve encryption process, key generation process, decryption process, signature generation process, key exchange algorithm, everywhere. Okay, because set of point is very important. That data point has to be arrived from some particular elliptic curve equation. So you will choose different types of equation, whatever you want. Okay, and then you can able to generate your own points here. Okay, okay. So after you generated the set of points, for example, you're going to transmit the variable a. okay, from sender to the receiver, okay. And for this again we have to consider one value here, the auxiliary parameter, okay. So the auxiliary parameter you have to consider, and that auxiliary parameter has to be shared between the transmitter and receiver, okay, before they go for the transmission, okay. And that is the assumption here, and that particular auxiliary parameter we need to take it, and then ASCII value for the message what you want to transmit. So you know that the ASCII value for A is 65, okay. So now we are going to find the points for the point A, okay. So this is a set of points what we generated, and based on that we draw the curve here, okay. And this is the formula here, okay. So to find the set of points, okay, so we are having a formula called R equal to M into K. So K is actually parameter, M is ASCII value of your text, okay, and then the receiver value is 130, and we have to go and check whether this particular 130 is present in the set of points or not. If it is there, means then you have to take the corresponding Y, and then we have to use it as a point for your text A. Suppose you are not getting the 130 mod for some 13 some value you are getting, okay. Suppose you are not getting that particular value, means then you have to then you have to go with other value, okay. So auxiliary parameter value, that particular value you have to choose, and then that particular value you have to apply in this formula, and then again you have to check whether you are having the excoded of the resultant outcome, okay. So if it is there, means then again what will happen, you have to take the particular value, otherwise what will happen, again we have to apply the K value, different K value. So like this what will happen, you keep on changing the value, and then you have to find your set of points for the alphabet A, okay. So once you do like this, okay, you can able to get the values here, and then you can go for the applying it in the encryption formula, okay. So this is the entire process of your elliptical cryptography. So what we did is we implemented the elliptical crypto system, okay, which is towards a prime core only, okay, and especially we implemented the Scala point multiplication. So not the entire encryption process, only the Scala point. Why we given more important for the Scala point multiplication is, if you implement the Scala point multiplication, definitely what will happen, similar structure only we are going to use it for the other operations like encryption, decryption, signature generations everywhere, okay. That's the reason, okay. So that's the reason we are focusing on the Scala point multiplication for the elliptical system, okay. So what exactly we did here is we implemented the double and odd always algorithm for Scala multiplication, because that will help you to overcome the simple power analysis attack. And also we implemented the Huffman compression technique. Why? Because is so whenever we talk about the elliptical cryptography, the problem here is we are having one message, okay. For example, I told that A is value I want to transmit from transmitter to receiver, okay. So that particular A value I am going to convert into plain text point. So plain text point is not the single value, it has 4 values, okay. So pair of points only we consider as a plain text point. So what will happen is, for single message we are having 4 ciphertext point, okay. So 4 means one single value, 8 bit is needed to store it in the memory. But if you go for pair of text, means 4 values we are going to store it. So 4 into 8, nearly 32 bit needed to store the single message, okay. So we what we think is we want to implement some Huffman compression technique or some run length coding method, or many things are there, okay. So many method, lump sieve encryption method, okay. So many encryption compression methods are there, okay. So we have to involve those methods. Then what will happen? Automatically what will happen? this 32 bit is again back to as the 8 bit. Okay, so that is the process here. Okay, yeah. So this is the software what we used here, and also this is the hardware we involved here. Okay, and this is the flow how we obtained the ciphertext message by involving the ECC. So initially the text message, and then that text message has to be encoded by the help of the goblets method, as I mentioned to you. So goblets method is the one which will convert your original message into the plain text point, and then that particular plain text point is going to involve in encryption process. Okay, nothing but encryption algorithm. There is a set of what you call it, set of formula will be there. Okay, that will be used to encrypt your message. Okay, by using the generated public key, as well as by using the message what is generated from the goblets method. Okay, and finally that will be given as input your Huffman compression technique, or whatever the compression technique what we have. Okay, and then it will be transmitted, and at the receiver side we have to decompress the reverse process of the compression technique we have taken care, and then we have to decrypt the ciphertext. Okay, and we have to decode the message, and we have to convert it into text message. Okay, and then we have to put it in the receiver side. Okay, this is what the flow diagram what we implemented using. We want to implement in using Vivado. Okay, Xilinx. But instead of focusing on other operations, only we focus on the point multiplication process. Okay, so as I told you, point multiplication process is nothing but it is operations of point addition as well as point doubling. Okay, so for this we have to give the input as a point. Okay, and then the resultant value is also come in terms of a point. Okay, that will be considered as your key for the encryption process, and also that will be considered for the plain text for the encryption process. Okay, so both will be both will have the role on your scalar point multiplication. Okay, so this is the encryption model what we developed. Okay, so in this encryption model, K and G, so K is a private key and G is any point, and there will be able to go, and that will be given as a point multiplication process. Nothing but point addition process has to come here. Resultant value you are getting C1. Okay, and similarly Q, A, P, okay, Q, K, okay, text. Okay, so these two are used for key generation, public key generation, and this is for your text to ASCII value, and then particularly the ASCII value is converted into message. Okay, encoding process by the help of goblets method, and then finally we are going to achieve the point addition process. Okay, that will give you the C2. So C1 and C2 are the two tricks we are going to get here. Okay, and this is the decryption model. So the decryption model, that C1 and C2 value we are going to give here. Okay, and we are going to involve the point addition, point subtraction process, and as a result, message decoding had to taken care, and then finally the message has to be converted into text by the help of the reverse process of your goblets method. So we implemented an encryption model as well as this multiplication model also, this multiplication model and then decryption model using Xilinx okay software, and then we obtained the better result in different FPGAs. Okay, so this is the elliptical look like, and this are the three important operations are involved here. And for encryption, for generation of public key, this is your public key generation process. Okay, and then this is a key exchange we have to do because after you generate the key, both users has to be known. Okay, then they have to share with each other, and this is the encryption formula. I told you some formula is involved here. So this is encryption formula, and this is the decryption formula. Okay, so for encryption decryption formula also we need help of our scalar point multiplication process, because Q is a point here, K is value here. Okay, And after this, what will happen? We are going to add with the M. So M is nothing but message is the form of point A. So these 2 points are going to add it with each other, and then we are going to generate a ciphertext point A. And then the resultant value M equal to you are going to give it as a input for the decryption. And again, see here, C1 is also point A, N is a number, okay, and we have to do some subtraction here, okay. So we have to take the convert into what you call as a 2's complement, okay, and then adding 1, okay, that will give you the subtraction of n values, okay, and that particular value is going to add with C2. So again, what will happen? Point addition operation has to be involved here. So as a result, we are getting the m value. This is not directly we are getting. We are getting the form of a plain text point. Then that has to be converted into original message by using the Goblet's method. Okay. So these are all the Vivado design flow, and this is a different process are involved there. And then we are getting the output like this. So I will show the output. Okay. So this is the inverse. Model multiplication inverse value for different values, okay, and this is the point addition formula already shown you, okay, point doubling formula, okay, and these are the values variables you are going to involve in this formula, okay, and giving this value 2 values, okay, p and q, and adding the values 3 and 6 for the a and value is 2 and 3, and the prime number is 37, okay. And similarly, different values were given for x and y for nothing but p and q, and then we obtained the value of how much the power, okay, how much the power is required here. So this much amount of 118.250 watt is needed for performing this operation, okay, and how many LUTs were involved, how many DSP processors are involved here, how many IO pins are used here, okay, and what is the buffer size, everything we shown here, okay, and this is your point doubling. Previous one is point addition, and this is the formula for point doubling. So point doubling 79.294 watt is consumed by the particular operation, and these are all the number of LUTs, all these things, okay. And also we implemented the what you call it as one is the encoding process alone using our Goblet's method, okay. So that is also we done. And we got the result. The encoder point is 224 for a particular value of your A, B, and N and M. Okay. Okay. So next, what we focus is we focused on different prime code and using different coordinate. Okay. So that is focus what we have. So elliptic curve scalar multiplication process, same process and same curve only. But what we did here is we are having 2 types of coordinates are here. Okay, so affine and Jacobian coordinates are there. So we will prove that these coordinates, okay, are which coordinates are suitable for the elliptic curve scalar point multiplication process, that we have to choose here. Okay, that will be first found, and then we will go for the implementation process. Like that we did. Okay, and also we did the same group operation process by using Vivado software here, and we also did how that particular coordinate is suitable for the which application, which type of application. Okay, that also we found here. Okay, so now we'll see this is the basic equation we have. Okay, and we implemented the inverse model as well as point addition model, point doubling model using affine coordinate as well as the Jacobian coordinate here. Okay, so after the implementation, we have to find that for which application, which type of coordinate are suitable. Okay, that we have to find here. Okay, so basic arithmetic operations involved in ECC using affine coordinate, Jacobian coordinate only I'm showing here. So basic operation is here for affine is multiplication, elimination operation, point doubling, point addition. Okay, and some come for here multiplication, and there is no inverse operation in your Jacobian coordinate. So if you involve a inversion operation, definitely what will happen? It will take some particular amount of time period. Okay, so we always prefer Jacobian coordinate compared with the affine coordinate. Okay, but some application wherever we need the inversion operation, okay, then in that case what will happen? Your more number of inversion operations are involved in this. Then in that case we will go with the affine coordinates. Okay, so this is the basic arithmetic operations are involved in our affine coordinate based ECC structure as well as Jacobian coordinate based ECC structure. Okay, and this is the addition formula, point addition formula. Okay, and for our Jacobian coordinate. Okay, and this is for your affine coordinate. So what is the difference is just the equations. Okay, the value or this number of variables involved in this formula is different. Okay, so see here over affine coordinate we are involving x1, x2 and the x3. Okay, y1, y2 and y3. Okay, but if you go for what you call this Jacobian, okay, so we are having three coordinate values: x1, y1, z1, x2, y2, z2. Okay, and then by using this, you can able to do the point addition as well as do the point multiplication. And also we drawn the data flow graph model. The reason why we drawn the data flow graph is easily we can able to identify how many addition operations, multiplication operations, inversion operations, subtraction operations are involved in the different layers of the operations. Okay, that is a major use of drawing the data flow graph model. So point addition and point doubling operation we involved in Vivado, and then we found that for bit size of 64 bit, it will take 256 clock cycle and time is 0.7 millisecond. Okay, and similarly point addition operation clock cycle is 351 and 2.05 time millisecond. Okay, but if you go for the Jacobian coordinate, okay, it will be given 172 and microseconds. In terms of microsecond we are getting. Okay, so the number of bit, okay, you are involving less, then automatically definitely what will happen, it will consume lesser number of operation time taken to perform the point doubling as well as the point addition operations. Okay, so that's the feature of, that is the best feature of your Jacobian coordinate. Okay, so next one is we are implemented the ECC for the image, okay, for the multimedia applications. Okay, so that is the next work what we did. So in addition to that ECC, here we are involving the DNA cryptography technique as well as the genetic algorithm also we are using for embedding the messages. Okay, and finally we found that how much the LUTs, DSP slicers, okay, are used to implement your architecture, entire architecture using the Vivado 2019.1 version. Okay, that is the work we did. So in addition to the replica cryptography technique, we involved in the DNA computing technique also, and also we are involved with the genetic algorithm method. Okay, so that's the reason we are given the name it as a hybrid cryptographic method we are given. Okay, so here as usual the role of your ECC is to encrypt your information whatever is given. Okay, and again it will be converted into ciphertext point only. But before that, what happened? We try to increase the level of security. Okay, to improve the level of security, we are going to add the other technique called DNA computing as well as the genetic algorithm. So that is another work what we did. Okay, and also we implemented using Vivado also. Okay, so what exactly here we did is we taken the plaintext original information. Okay, and we are going to not directly fed into the ECC for encryption process. Instead of that, we convert that particular to DNA nucleotide. Okay, so that is mapping table should be there. That particular mapping table are used to convert your plaintext into the DNA code. Okay, then that particular DNA code is going to convert it into binary value. Okay, then that particular binary value is going to involve in the genetic algorithm for embedding your or for hiding your information into the another image. Okay, this is something called as a steganographic process what we are doing. So reverse steganography is nothing but there are different types of steganography there: text steganography, audio steganography, video steganographies are there. So instead of instead of sending the images directly, okay, we are going to hide the information or hide the image, or we are going to hide the audio file with the information, or we are going to hide the text into the video, and then we are sending. Okay, that is the concept of different types of steganography here. And here we are hiding the text, okay, into the image, and that particular text is also not in the same form. We are going to convert it into the different form, nothing but DNA nucleotide form. Okay, DNA encoded form, simply called as, and then it will be transmitted. Okay, and it will be transmitted means not directed to the end user receiver side for the encryption process. Okay, for the ECC encryption process. Okay, and once the the hidden image, okay, or the stego image is encrypted, okay, and then what will happen? It will be transmitted. Okay, and again I told you already, if you involve the ECC encryption technique, definitely what will happen? Number of bits will get increased. Okay, when you go for convert your messages into ciphertext point, because for 1 8-bit we are going to get 32-bit as a resultant. Okay, so we need to apply some compression technique over here, and then we will transmit the particular compressed encrypted data to the receiver side. Okay, so that is also one of the new things we can able to add it in this particular proposed idea. Okay, to save the bandwidth also. Okay, that's the thing. Yeah, so here as I told you, there is a DNA table. Okay, encoder table will be there. That is helpful to encode your data. Okay, so we have the message, for example, hello. Okay, hello, how are you? Or simply hello. Okay, so that H value, that for the particular small h or capital H, whatever it is, first thing is we have to refer this table. Okay, for the particular H value, what is the DNA nucleotide? So here TTA is a DNA nucleotide. That particular TTA come here, T is 11. Okay, again T is 11. Sorry, 11 means 1 1. Okay, again another T is 1 1, and then A is 0 0. Okay, so that particular hello H is encoded as, see here, encoded as here TTA, and that particular T is encoded as 1 1 bit binary equivalent. Okay, 1 1, and again for A 0 0 is a binary equivalent. Okay, so these binary code only we are going to transmit as given as input for your embedding process. Okay, genetic algorithm is the embedding process. So what is exactly the genetic algorithm here is, so we are we are taken the what you call as cover image. Okay, and then we are having the messages in the form of binary digit. Okay, so now we are going to embed this binary digit into this cover image. So what we are doing here is we are involving the 5 different processes: horizontal scanning, vertical scanning, and then we do the mirror shift of the binary code. Again, we are going to perform horizontal scanning and vertical scanning. So nearly 4 processes we are going to do, and then we are going to find which process will give you the maximum matching bit. Okay, that we have to check using after we checking which is having the maximum bit matching bit. Using that particular method, we are going to embed the binary data into the cover image, and then we are going to given as input for your ECC encryption process. Okay, and the resultant values we are going to get as the encrypted stego image. Okay, this is what the entire what we developed for the wireless multimedia networks. Okay, so initially what will happen is the original message has to be converted into DNA nucleotide. again that particular DNA nucleotide again is going to convert it into DNA code. Then that particular DNA code is going to convert it into binary code. Okay, binary code, and that particular binary code is considered as a message bit. Okay, that particular message bit now we are going to embed into the one cover image. So you have to take the cover image. Okay, so cover image you know very well. So that is consists of pixels. Okay, image is nothing but arrangement of pixels in the sequence way. Okay, so that particular pixel value is taken. Again, that particular pixel value is going to represent the form of a binary digit, and then we are going to embed these digit, okay, with the cover image bit by involving either horizontal scanning method or vertical scanning method or mirror shifted horizontal scanning or mirror shifted vertical scanning method. As a result, we can able to know for some particular method we are having the larger matching bit. Okay, why we go for larger matching bit means in order to avoid the loss of data. Okay, so we have to find the larger matching bit. That particular method we have to choose and for our embedding process. Okay, then what will happen? That will be considered as the stereo image. Then that particular stereo image, okay, again is going to give us input for your ECC encryption process. Okay, for that you know very well we have to convert it into plain text pointer. So we have to apply here the obvious method and convert it into plain text pointer. And that particular point we are going to use the public key. Okay, and then we are going to do the encryption process, and then we are going to give the output as a encrypted stereo image. Okay, this is the entire process. So I'll give small example here. So hi is a text here, and this hi, ATC and AGA is a DNA nucleotide, and then we are going to use a binary mapping table to convert it into binary code. So this is the information what I'm going to hide into the particular image here. So this is the image. So this image is considered as the pixel values, and these pixel values are going to convert to DNA nucleotide. And each and every DNA nucleotide we have the binary code we have. Okay, so we are going to get the binary code. Okay, and this particular binary code only we are going to hide your binary bit here. Okay, so by using the horizontal scanning method, so we by using horizontal scanning method is nothing but we have to take your LSB of the plain text message, and then we are going to check it here. If both the bits are matching means then we have to leave as it is. If it is not matching means we have to mention the changes here. Okay, so like this what will happen, you have to find the number of matching bits out of the given binary code. So out of 5 bits are matching here. So by using the horizontal scanning, similarly 2 bits are matching here by using vertical scanning. Okay, and then we have to take the mirrored version of the plain text, and then again use your horizontal scanning 3/9, and then for mirror shifted vertical scanning we are getting 9/9. Okay. So vertical scanning will give you the best outcome. So using the vertical, see here for horizontal scanning, vertical scanning, okay, we are implemented, and then we got that how many LUTs and then how many DSP processes are involved here. Okay, for point addition, for point doubling. So everything we are obtained by implementing that particular algorithm in our Vivado software, and then we prove that. How much the LT is required to develop the particular system. Okay, so what is the use of the implementation is so that we can able to know that how much the CPU time, okay, how many LUTs are needed, okay, what is the memory space are required to perform your method. Okay, so those things you can able to arrive by the help of the implementation. Okay, I didn't show the most of the outputs here, only the few outputs only I shown here, because I want to share more information about other works what we can do. Yeah, so other one is the similar type of work. Okay, so elliptical scalar point multiplication using elliptical for prime number curve. Okay, so using that we are obtained the better throughput also, and then we are getting lesser number of LUTs, and then we are involving here P256 curve for our cryptographic algorithm here. Because compared with other curve, P256 curve will given the better result here. And other thing what we did here is we involved the modified as well as mixed Jacobian coordinate, because the last previous work we obtained the good amount of result in our Jacobian coordinate compared with the affine coordinate. But here we plan to do some modification in your Jacobian coordinate. Okay, otherwise initially we will use affine, okay, for particular process, and then later we'll go with Jacobian coordinates. Okay, so like this mixed type of coordinates also we use it here. So as a result of that, what will happen? We found that the process time will be very less, okay, compared with the others also. Okay, so the modified ECPM architecture will achieve only 28 microsecond time period for the for the curve P256 curve. Okay, so that will be standard curve will be there. We are using that particular curve. For the particular curve, what is the curve is already told you. That is set of equations will be there. Okay, that will help you to perform the operations like point addition as well as the point doubling operations like that. Okay, so this is the set of formula used for your P256 curve. Okay, and the prime arithmetic operations involved in this particular P256, this one, and then this is for a modified Jacobian coordinate. So we made small modification here. Instead of x, we use s by z squared. Instead of y by z cubed. Okay, so like this we made small changes here. Okay, and then that particular modified Jacobian coordinate only we are using for the implementation. Okay, and we drawn the data flow graph model. So we know that it will require very lesser number of addition and multiplication operation for your modified Jacobian coordinate. This is for the point doubling. Previous one is for the point addition. This is for the point doubling formula. Okay, and this is the data flow graph model. So easily you can able to count how many number of addition and subtraction operations are involved in a thing. Okay, and this is the entire architecture what we created for our ECPM. Okay, nothing but point doubling. Okay, point addition. Okay, all the things are carried out by the help of single architecture here. So here we are involving four mux. Okay, four mux here, and then two counters. One reset will be there. Okay, as well as one counter will be here. Okay, so with this we implemented our modified ECPM architecture. After implementation, we are getting the better result. Okay, this is a point addition, point doubling. So we obtain better results, and also we found that this will require a very lesser amount of process time to execute your ECPM structure. Okay, and next one is AES based authentication algorithm. So here AES algorithm we are using, not the easiest algorithm, because some particular applications we need the fast, okay, as well as high speed authentication things we needed, some IoT based applications. So that's the reason. Just a minute.
Harivarāsanam Swami Vishwamo
Just a minute. Yeah. So, okay. So here we implemented AAS algorithm. So I hope I'm audible to you. Yeah. Okay. So yeah, you know that the AAS algorithm will involve a different number of rounds. Okay, to do the encryption process, and also the involving some block size of keys to do the encryption process. Okay. So in addition to that, we always involve here secure hash algorithm to determine the data integration as well as comparison checking here, because that is the one we use to maintain the integrity here. Okay, so the total number of message bit, and we are going to add it with the hash code, and that particular hash code is going to check it at the receiver side for the encryption for the checking purpose. Okay, that is the work what we did, and we also implemented using Xilinx software. Okay, and we proved that it will given you the lesser amount of time period, okay, for execution, as well as lesser amount of LUTs are involved here, like that. Okay, yeah. So okay, first one is we are having AES based authentication scheme. It has SHA-1 as well as AES algorithm. So it has two parts, transfer and receive parts. Okay, so see the plain text here, and this plain text is going to involve in two cases. So one is in generating your SHA code, as well as other for the encryption process. So for encryption process, we need 120-bit key size. So that is going to give us input here, and we are going to get the ciphertext of the message, and these ciphertext is going to append with your hash code, and resultant hash code is going to send it to the receiver side. Okay, so if during the transmission, if anything happen, okay, if anything happen means, suppose they will check the they will change the ciphertext. Okay, and simultaneously what will happen, the what do you call it, the hash code is also will changes here. Okay, and the resultant hash code what we generated at the receiver side will have the change. Okay, so we have to find the method to detect the what is the change in the code, and also we have to know what place the changes will be. Okay, that is a different algorithm will be there. Okay, to check the number of errors, okay, number of bits, okay, that are different algorithms will be there. What we focus here is whether they are going to authenticate the device or not. Okay, that is the thing. So encryption is done by the help of AES, and then authentication is taken care of by the SHA code. So we have to generate the message authentication code by the help of the SHA algorithm. Okay, and then we are going to append with your ciphertext, and then we are going to send it. At the receiver side, we have to split your message authentication code as well as the cipher. Just a minute, I switched on my laptop. So meanwhile, you have any queries means please ask. Yeah. So it takes some time. Yeah. So what we did is, we split our ciphertext as well as with our SHA code, and then the whatever the text what we splitted, that again will undergone for generation of the MAC code. That particular generated MAC code is going to compared with the received MAC code. If both are equal, okay, then only what will happen, we will accept the device. Otherwise what will happen, we reject the device. Okay, so that is work we carried out. Just a minute, I will rejoin again. Yeah. So after implementation, so this is your result. Okay. So plain text as well as a key. Okay, as well as the hash code whatever we have here, and then similarly here the A is decryption, and this is the key what we use it there, and this are all the schematic view of, and after we implemented different FPGAs. Okay, we got how many slices, how many LUTs, okay, how many IOBs are involved for implementing this AES along with the SHA code, and different FPGAs Okay, diagram, the same thing, the terms of diagram. Okay, and there are some constraints also will be there. So if you go for because if you go for SHA-1, we are definitely what will happen, the question attack will be there. And if you want AI security, we have to involve more number of keys. So if the key is tampered means what will happen, whole key is compromised here. So we need to increase the length of the key. If you increase the length of the key means automatically the security will be high, but what will happen, it will give the more computational power. Okay, that is the problem here. Okay, and this is overall cost what we involved in our AIS. Okay, so this is what the work we did. Okay, so any
So, everyone, on behalf of RF and Communication System Department, we would like to extend our heartfelt gratitude to Dr. Vijay Kumar sir for sharing his deep insights on cryptographic algorithm. Sir, your session was truly enlightening and enriched our understanding of secure hardware designs and its relevance in modern day applications. So, once again, we are thanking you, sir. Thank you, participants, for your joining this activity.
thank you, ma'am. Thank you.
Thank you, sir. Yeah.
Can I leave, ma'am?
Yes, sir.
Hello. You can share the feedback, madam. How much, madam? சரி என்ன வாங்கிட்டு வரானா இல்லையா? நான் சொல்லவே இல்லை. சொல்லு. இல்லை நான் வாங்கிட்டு வரவா? சுகர் வாங்கணும். காலி. வேற என்ன வேணும்னு சொல்லு.
வந்து 7:40 எப்படியாவது அந்த 8:30 போயிட்டு வரணும்.
வேண்டாம்.
9 மணிக்கு வந்து செஞ்சு 10 மணிக்கு சாப்பிட்டு படுக்கேன். அப்படியா?
அதனாலதான் சொல்றேன். ஒரே ஒரு நியூஸ் பாருங்க.
அப்போ 1:30 மணிக்கு நீ எத்தனை மணிக்கு சாப்பிட்ட என்ன சாப்பிட்டேன்னு எனக்கு தெரியாது. இத்தனோடு சோறு சாப்பிட்டு அவன் வெளியே சாப்பிட்டு அப்ப எல்லாரும்
நானும் அதை சாப்பிட்டேன்.
Thank you.